Now let's talk about continuous random variable. Before this, we were talking about discrete random variable. So let's say you have a continuous random variable x, right? And it can take any value in on the real line. And let's say sometimes it is in a fixed interval from a to b. Sometimes it can be from minus infinity to plus infinity. So for this particular variable, for it to take one exact value, the probability is going to be 0, right? So probability of, let's say, x equal to x, okay, is equal to 0. Why? Because let's say one of the most common distributions that you might have encountered is the Gaussian distribution, right? So let's say this is the Gaussian distribution, this is x, this is p of x, right? So you can think of any particular exact value, the probability of that exact value is 0. So let's pick the value, let's say 170, right? So and let's say this is in centimeter and this is heights of people. So for someone to be exactly 1 centimeter, it's going to be a very infinitesimally small probability. The person could be 169.99, or they could be 170.01 or something along those lines. There'll be some off, but because of rounding off, it may get rounded off to 170. But exact value having height 170 centimeters is pretty much the probability of that is 0. So how do we represent probabilities in that case? We represent it using something called a PDF, probability density function. Okay, so the probability density function, it's a continuous function, and its value at any given point can be anything, in the sense that it has to be greater than 1 though, so greater than 0. So we'll represent it using a small p. Okay, p of x is greater than equal to 0, and integration of p of x from minus infinity to plus infinity is going to be 1. So the area under this curve is going to be 1. Alright, so the only way to define probabilities on this curve, not probability densities, probabilities, is based on intervals, not single values but intervals. So I will take an interval and I will say that the area in this interval is the probability. So let's say this is A, this is B. So the area is the probability that A is less than equal to X less than B. Okay, so the probability is in areas, not in the values. So this value is not a probability, it's a probability density. So density means that if you take a fixed, infinitesimally small fixed interval delta x around x, right? So having high probability density means relatively in this value of x, if I take delta x around it, you will have relatively high probability than if I take delta x around this value of x. Okay, so this area is smaller than this area, provided the gap is the same. The delta x gap is the same. So you have to divide it by delta x and take the limit of delta x tending to 0, so it becomes a density function. So for continuous random variables, we don't define PMF, probability mass function. We define probability density function. So for both discrete random variables and continuous random variables, we can define something called, so for continuous random variable, we will define something called cumulative density function. Okay, which is basically the running integration of this probability. So this is basically minus infinity to x, p of x, y. I'll use a different variable, so that's why I'm using y, because the y is running from minus infinity to x. So this cumulative PDF, if I plot this, if you plot the integration of this up to the point x from negative infinity, what you will get is you will get some 0 value, and then it will saturate to 1 value because it all integrates to 1. So this will saturate to 1 and it will start from 0. Okay. Similarly, for discrete random variable, we will have cumulative mass function, and that will look similar to this, except that it will have steps. So it will start with 0 and ultimately it will reach a step of 1. Okay, so it will start with 0 at minus infinity. Where will it take a step? Wherever the value of that variable is. So let's say 1, 2, 3. Okay, so this was for and let's say for 0 it was some small value, and then before that it was 0. So this is an example of that binomial distribution that we were talking about. So for binomial distribution, we will have a cumulative mass function, which will also go from 0 to 1 in steps. So you can think of these steps when you differentiate it instead of so these discontinuities cannot be differentiated. Instead, you will get Dirac delta function at those points. So now let's talk about some useful probability density functions. The most common is the normal distribution, which is also called Gaussian. Remember, it's always with a capital G because it is a proper noun, comes from Gauss. And when you are writing normal, n need not be capital. So Gaussian or normal distribution, here usually we use this stylized n to represent it, of x, okay, either given or we will use a semicolon. So it has two parameters, mu and sigma. Mu is the mean or the expected value of this distribution, and sigma is the standard deviation or the square root of the variance. Okay, so this is going to be defined by this formula. We will have 1 by 2 pi sigma square root, okay, then e to the power minus x minus mu whole square by 2 sigma square. So this entire thing is in the exponent. So the way it is plotted is you will have some mu, around that you will see the bell curve or the normal curve. At plus infinity and minus infinity, the density will go down to 0. Here the density will be maximum. Okay, and there will be a spread parameter, how wide this bell is. If the bell is wider, then the top height will be lower. If the bell is narrower, if the width is narrower, then the top height will be large, so that the area is always equal to 1, and this constant ensures that. Okay, so here now you can relate that to this formula, that how x minus mu, so when x is equal to mu, at that point you will get e to the power 0, which will give you the maximum value. Otherwise, e to the power some negative number, which will give you lower values. So for plus infinity or minus infinity, you will get e to the power minus infinity, which is 0. The other thing to note is that with these uh, continuous PDFs, right? There are other things that you can do that are similar to what you would do for a discrete random variable, where instead of summation we'll have integration. So here h of x, okay, this is the entropy of x, will be defined as integration minus infinity to infinity, okay, and it is going to be expected value of log of px. So it will be log px uh, px dx. In general, expected value of any function of x is going to be integration of minus infinity to infinity f of x px is the density function dx, and expected value of x itself, okay, is going to be integration of x px dx. So if you plug uh, the Gaussian density into this formula, what you will get is expected value of x is mu. Okay, that is the average value or the expected value of x. Similarly, you can find variance of x by taking expected value of x minus x mean of x whole squared. Uh, so this is a separate detour. Let me box it so that it's clear that this is applicable to all probability density functions. I'll just talk about one more probability density function, and that is the beta distribution. A beta distribution is defined for x within the range 0 to 1. Okay. So let's say usually this is for, let's say your x can take some binary values. It's a binary random variable, but you want to play that it is concentrated towards 0 and 1, or it is concentrated in the middle, and so forth. So there are different ways to define this beta. You can take it can take all sorts of shapes. For example, it can take a shape like this, which is skewed towards the left. It can take a shape that is skewed towards the right. It can take a shape that is symmetric. Okay, it can take a shape that is U-shaped. It is more concentrated towards the ends. But all of these will integrate to one. Okay. And to get all these shapes, you need two parameters. Uh, and You need two parameters A and B. Okay. And basically your beta distribution of x given AB is defined by uh, gamma function of A plus B divided by gamma of A, gamma of B, okay, x to the power A minus 1, x to the 1 minus x to the power B minus 1. Yeah. So here, one thing to note is that A and B have a symmetric role, and this is only defined, by the way, this is only defined for x belonging to, this is for only for 0 less than equal to x less than equal to 1, and otherwise the beta distribution is 0 otherwise for other values of x. So why this gamma distribution? Because this is a normalization constant. We want the function to integrate to 1. So if you integrate the rest of the function, this portion of the function, what you will get is the inverse of this constant. You will get gamma a times gamma b divided by gamma a plus b. So now to make the whole thing 1, we take the reciprocal and multiply this. So a lot of these constants come from making sure that these functions integrate to 1. So A and B have sort of a symmetric role around 0 and 1. Uh, if you want the same shape but in a mirror image, you would exchange what you're doing with A and B. Another important distribution that you can have uh, for continuous random variables is a uniform distribution. Okay, and it will be over some interval a to b. Okay, and usually we take it from 0 to 1, but it can be for any interval a to b, and the height of it would be 1 by b minus a. Okay, so that the area integrates to 1. I can leave it as an exercise to find what is the expected value. That is it indeed a plus b by 2. Sorry, a plus b minus a by 2, right? Okay. Now let's talk about multivariate probability density functions. Just like we had joint distribution for two different discrete random variables, we can have joint distribution for multiple continuous variables. In fact, we can also have joint distribution for a discrete variable and a continuous variable, but we will come to that when we actually talk about some techniques in machine learning. How now let's just concentrate on uh, two continuous variables. So let's say you have variable x1 and x2. Okay, so we will define their joint probability as p of x1 x2. Actually, we'll not define the probability, we'll define the probability density. So again, it has no a single point should not be interpreted as probability. Going back here, I want to remind you that for normal density, this peak, for example, can be above 1. Similarly, this 1 minus b by a can also be more than 1, right? And similarly for the beta distribution. So probability more than 1 doesn't mean anything, but probability densities can be more than 1. They just have to be greater than or equal to 0. Okay, so similarly here, what we will do is we will, let's say, draw a two variable graph. So we have x1 and x2. But now, how do we define this density? How do we draw it? It will be coming out of the paper, okay? Because at most it can be on the paper or the screen, which is 0. And that third dimension we will draw as contours. Okay, so let's say it can have contours like this, such that the area inside this the volume that is contained in this hill is 1. So this will integrate. So the only condition that we have is that p of x1 x2 is greater than or equal to 0, and double integration of p of x1 x2 dx1 dx2 from minus infinity to infinity minus infinity to infinity will be 1. Okay, so this is the definition of this probability density function. Another way to define this would be to just call it, make it into a vector. Okay, so this will be bold character. Okay, so where x is equal to, it's a vector of x1 and x2. It's the same thing. So it's another way of compressing the notation by using vector notation as opposed to spelling out each variable separately. So now let's extend some of the concepts that we learned in continuous variables to the discrete variable. So let's say I want to find out p of x2 given some value of x1 equal to some value, right? So x1 is equal to a, right? So the way to do this would be that, let me choose a color, p of x2 given x1 is equal to a. So I will choose this value a. Okay, at that point I will draw a slice because x1 can only take that value, and then this slice I will project. Okay, and this slice, if I project it onto this x2 axis, it will look like, let's say, okay, it will look like perhaps something like this. And the area under this slice with just the projection need not be 1, so I will normalize it so that it becomes 1. Okay, so that normalization I'll have to do. So basically this is going to be p of x1, okay, p of x1 is equal to a and x2, all right, and divided divided by p of x1 equal to a. Okay, so this is the conditional density for a continuous random variable when it is conditioned upon another variable. Similarly, this just the p of x1, we can define that. So let's say if we want to define p of x1, okay, this will be based, this is the marginalized, so this is conditional, and this is the marginal. So what do we have to do in the marginal? We have to eliminate the other variable, which is x2. So we will integrate over all values of x2, and we will take p of x1 x2, okay, dx2. Okay, so that is the marginal, the way you will compute the marginal. Now let's talk about an important multivariate distribution, which is the multivariate Gaussian distribution. So this distribution is such that, again, let's draw it for x1 and x2. It's such that it is Gaussian in both x1 and x2, okay, and in the sense that the marginals are Gaussian, and it is also jointly Gaussian for both. So it looks like its contours look like elliptical, okay, where the maximum density is at the mu, but this mu itself has two values, two coordinates, mu1 and mu2. So this is mu1, this is mu2. Okay. And you can see that there is a direction here and a normal direction here. So this direction need not be axis aligned. So the easiest, the canonical form of this distribution is when it is concentrated. It's mu1 and mu2 are both 0, and it's it is isotropic Gaussian, and it is that means in the if you go in any direction, the density will drop off in the same manner. You can take any slice going through the origin. You can take any slice going through the origin. It will basically have the same Gaussian density. Okay, so that's a canonical form, but you can actually shift it to some non-zero position, such as some arbitrary mu1 and mu2. Plus, you can squish certain directions and elongate other directions. So that squishing and elongation is defined by the sigma, but here the sigma is going to be a matrix. It's not going to be a single number. Okay, so this sigma is going to be a matrix, that is a covariance matrix. So you will have sigma 1 1, okay, sigma 1 2, sigma 2 1, sigma 2 2. So these two are the same. It's a symmetric matrix. Okay, so if the off diagonal terms are 0, then it is going to be axis aligned. So that means it is going to be uh, its elongation is going to be along the axis. So if sigma 1 2 and sigma 2 1 are equal, then it is going to be like this, or it will be like this. Okay, it will not be tilted. If sigma 1 1 and sigma 1 2 are non-zero, then you can have tilted ellipses. Okay, so what's the entire formula? The entire formula is the following. Sorry, these are squares. Okay, these are squares. So these are the cross covariance terms, and these are the variance terms of the individual variables. And this can actually go to 3 dimensions, 4 dimensions, n dimensions. So let's say it goes to k dimensions, then your PDF p of x. So here I will draw a bold x because it's a vector. It's going to be 1 by 2 pi, okay, to the power kth root, k by 2 root. K is the dimension, okay, k by 2. All right, and then determinant of sigma, yeah, this is also in the denominator, determinant of sigma square root, okay, or you can write the whole thing as 2 pi determinant sigma. Here it is to the power k, and then there's a whole square root. Okay, and then you will have times e to the power, now here pay attention, it is going to be minus half, okay, times x minus mu vector. These are all vectors. X minus mu vector. If I'm taking e to the power something, I want a scalar, so I have to make this x minus mu vector into a scalar using some other terms. So this will be transpose, and then 1 by sigma becomes 1 by sigma square becomes this sigma inverse. So it's a matrix. It's also a 2 by 2 matrix or a k by k matrix, and times x minus mu. So this is when I take the transpose, the dimensions of this is 1 by k, dimensions of this is k by k, and dimension of this is k by 1. Okay, so now you multiply all of them, you will get 1 by 1. Okay, so that's a scalar that we want. So this is what is in the power of e. Here again, when x minus mu is 0, when x is at mu, then your exponent will be 0. And this constant 1 over 2 pi k determinant of k square root, that ensures that when you integrate over all dimensions of x, you will get 1.